Welcome back to most of you. How many first-timers here, if you can raise your hand? We've been doing this for 14 years, and this is your first time you figured this out. Welcome, one and all. This is the first time that we actually have a triple sellout. You're apparently the lucky ones to get the main venue. There's spillover into our next largest room, and then spillover into the next one. And not only that, we are live streaming on the internet. So a lot of people will participate in this 14th annual Isaac Asimov Memorial Debate. I want to publicly thank Janet Asimov, Isaac Asimov's widow. Those of you who might not know, Isaac Asimov he wrote more than 300 books, and much of the research that went into his nonfiction books, and perhaps some of his fiction books, was conducted in the research libraries of this institution. And so there's a connection that we have with him that few other institutions had. And his family decided that we would conduct this annually in his honor. Isaac Asimov, perhaps the last polymath of our civilization. So I want to publicly thank and acknowledge Janet Asimov on that. Tonight's subject, as you have surely gleaned by now, is nothing. And the existence of nothing. And the program, just so you know, we weren't running out of toner, all right? We were trying to figure out a way to have the title become nothing. So this is our attempt to capture that fact. There's nothing wrong with your program. Since we last met, an asteroid struck Russia, the Curiosity rover plunked down on Mars, the Higgs boson was discovered. The universe has been a busy place. A lot does happen in a year, and it's just great to have all of you back each year. The subject of nothing. I don't know if George Gershwin wrote the first song ever on the subject of nothing, but in Porgy and Bess, the title of the song was, "I've got plenty of nothing, and nothing's got plenty of me." And so nothing, of course, has been on people's minds a long time. Actually, back then, the words of that song would have been uttered, "I got plenty o' nuttin'." That's how they were written. Times have changed, haven't they? My parents are here this evening. They're 85 and 84 years old. I just want to publicly recognize them. They brought me here as a child at age 9, my first visit to the Hayden Planetarium here as a native of the city. And today, I am the Frederick P. Rose director of the same place that launched me on this epic voyage of discovery. So those are institutions operating at their best. They brought a friend with them, Heidi Sweets is her name, and they forwarded me a poem she wrote on nothing. I felt compelled to read this before we begin, to set some of the mood of the evening. Nothing speaks volumes. Imprisoned dreams, jailed forever, forgiveness weeps. No tears are released. Silence begs for ease. Anger has no hope. Indifference rejoices, while nothing holds court with jesters of time. Nothing waits and waits. Thank you, Heidi, for that contribution. Written before she even knew of this panel. Let's bring out our guest and get the party started. My first guest is a professor of physics at Stanford University, professor of theoretical physics, that is. Don't know if she's ever even visited a particle accelerator, but she tells him perhaps what to look for. Professor Eva Silverstein. Eva. Next, we have our first time ever three-peat. We have the physicist and professor of Earth and space exploration, Lawrence Krauss. Lawrence, come on out. Lawrence was in the first ever Asimov debate. The fact that he's been here 3 times means he just always works on controversial topics. Hence, we always reach for him. My next guest, a longtime colleague of mine during my days at Princeton, is J. Richard Gott III. He's professor of astrophysics there. Rich Gott, come on out. Rich, you brought a shopping bag. I don't know what you got going there. Well, maybe we'll find out later. I'm almost afraid to ask. Reminding you that this is a debate about nothing. So, next, we have a longtime writer, contributor to major publications, and his specialty on the topics on which he writes is the intersection between physics and philosophy, Jim Holt. Jim Holt, come on out. Thank you. And last, and I was going to say not least, but it kind of is least because this guy is the world's expert on zero. Charles Seif, come on out. He's professor of journalism, New York University. So the way this works is you are eavesdropping on a conversation the 5 of them will be having that I will be steering. All right, these aren't lectures, these are not, it's kind of just see what we would talk about if we were at a bar. That's really how this works. We've done this 14 years in a row, and we have a fun time doing it, and I'm glad you're here to join us. So each of the 5 panelists will start out with like 1 or 2 minute remarks, just so you can hear their voice and get a feeling for how they speak, and then we'll jump right in. So Eva, please, let's begin with you.
So let me just say that one of the greatest results in all of physics, I think, is our understanding of how structure in the universe formed, starting from quantum fields that for all practical purposes were in their ground state, in their vacuum state. And that, combined with the inflationary expansion of the early universe and quantum mechanics, leads to the origin of structure that we see today. And just last point about this for now is that one of the most interesting features that we've learned about this more recently is its sensitivity to very high energy physics questions that bring in problems of quantum gravity, and which on the one hand, and which on the other hand are accessible through some observations of the microwave background radiation. So to me that's the most interesting version of nothing that I know.
So you're saying when you say it's sensitive too, you mean possibly experiments can come and have a bearing on your theoretical meanderings?
Indeed. So the inflationary theory is subject to probes. In fact, there's one coming out tomorrow that's very relevant. Tomorrow,
so we're one day too early. But we did get to hold today on the vernal equinox, right? Just so you know. Happy spring to everyone. And those of you on the internet, if you are the 15% of the world's population who lives south of the equator, happy autumn. Okay. And that would include 100% of the world's penguins. Happy autumn to penguins. Free penguins, that would be. Lawrence, please reintroduce yourself to everybody here. Thanks for coming. Just off the plane from Sweden, by the way. Lawrence, thanks for coming in a third time.
It's always a pleasure to be back and to have fun here. Well, obviously, I've thought a lot about nothing. I've written a book about it recently, but I think that the most exciting thing, there are 2 things. First of all, that we've learned that most of the universe is nothing. Nothing is the most important part of the universe, so you're all more insignificant than you thought. And the second thing is that if you asked, and one of the things I find most amazing is if you asked what would be the characteristics of a universe that was created from nothing by just natural laws without any supernatural shenanigans, it would be the characteristics of the universe we live in. And that I find amazing and worth celebrating, because it makes God more redundant than God was before. And the other thing I guess I want to say before I end is I think Jim, who I greatly admire, I expect will will disagree with some of the things I want to say. So I want to say right off at the beginning, but for those people who are old enough and understand the spirit of what I'm about to say is...
Wait,
Jim,
you want to
you're
start
an
a fight already? We just,
well,
these are
hold
just
on,
opening
Just
remarks.
Neil, let me finish what I'm going to say before you interrupt. You'll interrupt later. So I just want to say, Jim, you're an ignorant slut. Okay.
For those born before 1960, that's an expression on Saturday Night Live uttered in
Exactly. I didn't mean
1975.
anything.
Yes. Next, Rich Gott.
That's how it's going to go. I'm Rich Gott. I work on general relativity and cosmology, and I discovered an exact solution to Einstein's field equations for a cosmic string and for then two moving cosmic strings. And that was interesting because it allowed time travel to the past, like several solutions that are known. Kurt Gödel found one in 1949, and then there's the wormhole solution. I'm wearing a coat tonight that Bob Kirshner called the coat of the future. He said, Richard, you must have gotten this coat in the future and brought it back in your time machine because this color hasn't been invented yet. So whenever I'm talking about time travel, which I will a little bit tonight, I wear this coat. So I'm relevant to tonight. Li-Jing Li and I worked on a quantum vacuum state that we thought might be relevant for the creation of the universe. We'll say more about that.
Okay, excellent. Thank you. Jim Holt, what have you got for us?
In the light of Lawrence's, or may I call you Larry, your ungallant allusion to me, I am not ignorant. I'm going to spend most of my breath attacking you, and I'm going to attack you from the left. You are an avowed militant tub-thumping atheist, and the old equation that we have that we inherited from Christian metaphysics is that God created the world out of nothing, so it's God plus nothing equals the world. And you take God out of the equation, and I'm all for that. But so now we have blank plus nothing equals the world. And what you put in the blank is the laws of nature, the laws of quantum field theory. And I think that actually in worrying too much about the problem of why there's something rather than nothing and trying to find something to put in the blank where God used to be, you're actually still in thrall to Christian metaphysics. And I think you see the laws of nature, particularly the laws of quantum field theory, very much as divine commands. So I think you're shall we say, insufficiently enlightened.
Oh,
How dare you be so rude? Why, no one's ever said that.
We'll revisit this. So, Charles, Mr. Zero.
I don't know how I'm going to follow this.
Wait, we get his microphone working over there?
Hello, testing.
They turned it to 0, I think.
You are so full of Zero. Why don't you borrow this?
I'm Charles Seif, and I think I'm just here to fulfill my father's prophecy that I'm good for nothing. I was born to be a mathematician and didn't wind up that way after studying mathematics for a while. I wound up in the Economist building in London and realizing that, hey, journalism is a lot more fun than sitting in your office doing the silly of not invariance. So I joined the circus, became a journalist, but of course my mathematics core was still there, and my first book was about math that I loved, and perhaps the most fascinating thing I encountered during my studies was zero.
Cool. So I'd like to start with you. Test your mic one more time.
Testing 1, 2, 3.
Yeah, he works now. Good, thank you. So I just want to start out with you. Zero, it seems to me that was that people's first attempt to quantify nothing, to turn nothing into something? Because, of course, in case you never noticed, Roman numerals cannot represent 0. You ever thought about that? There is no 0 in Roman numerals. So ancient Rome and their huge and great civilizations precedes the invention of zero. Is that right?
That's absolutely
That's
correct.
right. So what took so long?
Well, we humans had a real revulsion for nothing, for void, for emptiness.
Don't we still? Was it then and not now?
Oh, it's still here. It's still here, although it's diminished somewhat. I think it's because, in part, we humans have.
I think that's what you said. We humans.
We humans.
Okay.
Am I including people that I shouldn't?
No, that's okay. No, we're good. We humans, go. I just like the phrase. Go.
For us, nothingness represents something that we're afraid of, that disorder, a breaking of the rules. That one of the things that we humans do is we control our environment. And the way we control our environment is through imposing order on things, by figuring out the way things work. And zero represents, in some ways, nothingness represents a return to the lawlessness, the primordial ooze without rules. For example, if you look in the Bible, the Hebrew Bible, the creation myth starts...
It's the Old Testament to Christians, okay? Just so you get the... Go.
The creation was out of nothing. If you read the Hebrew, it says the world, the earth, was formless, chaotic, and void. And it's not a coincidence that chaos and void were twinned, because the void represented a lawlessness, a breaking of the rules, that how could something which was nothing have any rules that defines what it is, how it works, how it behaves? And by breaking the rules, it became scary.
But the primordial chaos was not nothing. It was a disordered something. I mean, the Hebrews...
I got to go with Jim on this.
The ancient Greeks didn't really have a concept of absolute nothingness. They thought of the things began in chaos, and order was imposed in chaos, and chaos became cosmos. But it wasn't. It was only with Christianity, I think, that the idea of creation ex nihilo came to
Out of
be
nothing.
formulated. Yeah.
Okay.
Because the idea was that God was so powerful, was so all-powerful, he didn't need any pre-existing material to create the world.
In fact, it actually comes from way before the Greeks. The Rig Veda, all of it didn't have creation from nothing. It was creation from some primordial stuff.
Yeah.
Often water in a lot of the creation myths, but primordial stuff.
Yeah.
As opposed to the real nothing, which is what I'm going to talk about.
By the way, the Hebrew term for that in the Bible is wonderful. It's tohu bohu, which...
and actually the tohu is the chaos.
Okay. So
Chaos.
what's the
And
bohu?
bohu is actually a very difficult word in Hebrew because it was used, I believe, 3 times in the Bible. And it is believed to mean void.
Okay.
In the true sense. I mean, it may not have been exactly...
Well, that's
what
why, because today when anyone uses the word chaos, we're not referring to a place where nothing is happening. We're referring to a place where everything is going on, but just in a disordered state. So the modern use of the word chaos is not consistent with nothing, I would say.
But that's the whole point, I think, is that the ideas of nothing have changed since these vague, ill-defined notions, and that's good. It's not a bad thing. It's called learning.
Well, however, but in the Hebrew Bible, we presume, regardless of whether there was are we saying the void and the chaos preceded the formation of the universe, or was that just the early universe as described in the book?
Well, it's actually ambiguous, because if you looked at, say, the Septuagint, one of the versions of the Bible, that in fact there's an implication that there was a previous creation, and that there was a creation out of nothing, the chaos of the previous creation. But in the Bible that we use, the Pentateuch, it is the use of the past implies that this is the first creation out of nothing.
So Jim, when did philosophers start weighing in on this?
Really with Leibniz in the 17th century. He was the first thinker to pose the question, why is there something rather than nothing? And by nothing, he meant a state in which there are no existence at all. There are no entities, there's no chaos, there's no space, no time, absolute nothingness. It's very difficult to grasp in the imagination. If you try to obliterate all of the contents of your consciousness, or try to imagine all of the contents of the universe slowly being extinguished, the stars going out, the atoms disappearing, life disappearing, time and space disappearing, It's interesting that the son of Samuel Taylor Coleridge, Hardley Coleridge, as a child, had precisely this intellectual struggle. And he said, and I imagined, all of this disappearing, all the grass and the stars and the people, and there was nothing but dark and cold, and nothing to be dark and cold. So that, that's the best you can do. And even when you try to reach nothingness in your imagination, there's still, the little light of your consciousness, creeping under the door. The only times I've succeeded in imagining absolute nothingness is two times. Once
But
during,
you've succeed.
Yes, once during...
Under what
Actually,
influence?
every night during dreamless sleep. And once while I was watching professional bowling on television.
Okay. Not a bowler, I would guess here. Okay. Leibniz, but
Leibniz.
Excuse me, Leibniz. I'll give you space to hypothesize here. Would you say that his thoughts of nothing contributed to his invention of the calculus? Or put him in a place where, because Leibniz as well as Newton, sort of co-separate inventors of calculus, almost contemporaneous. So do you think one of those had to do with the other?
Yeah, well, the crucial notion of the calculus is the notion of the infinitesimal, the infinitely small. And what is the infinitesimal? It's not nothing, but it's not quite something either. It somehow mediates between finitude and nothingness. So, yeah, I think you have to have a sort of a temperamental attraction to dangerous ideas. The infinitesimal was considered to be an extremely dangerous idea, and there was a great resistance to the calculus because of it. And I think that...
why is it dangerous? You keep putting these terms
It's dangerous
in
because it sometimes it acts like a zero, and sometimes it acts like a
Why does that
finite
make
number.
it... It's just weird.
But
It's
you
not
can divide
dangerous.
by it, which is always, if you're by
look,
dividing by zero, then you get mathematical chaos.
I think that what Jim has pointed out is exactly it. Is one of the limitations of philosophy, really, is that, if you'll forgive me.
I'm a journalist,
is
not a
that-
He
philosopher.
won't forgive you,
I don't
but just
care.
keep talking.
Okay. Is that you're absolutely right. There are some things that are essentially impossible to get an intuitive conception of, and that's just a limitation of the fact that we're classical human beings who didn't evolve to understand, to intuitively understand quantum mechanics. So there's lots of things in science that are impossible to get any intuitive handle on, but that doesn't mean they don't exist.
I completely agree with you. And I think that a state of absolute nothingness, even though we can't envisage it in our minds, it's logically consistent, it's a real possibility, and there is a genuine question: why is there a universe rather than absolute nothingness?
Well, let me take that to Rich Gott here. Rich, you've done a lot of thinking about the early universe, about the expansion of the universe. You're a universe guy, you're a cosmos guy. And at some point you had to wonder what was outside of the cosmos itself, or what birthed the cosmos. If not from nothing, then what?
Well, okay, let me go talk about what he just said. Let me try to give you an idea of two different kind of nothings that we're going to talk about. And since I'm a visual guy,
Wait, so there are two kinds of nothing.
There are two kinds of nothing we're going to be talking about tonight.
I'm going to talk about three.
He's got
Three.
a
You got a
third
fourth
one.
over here? Sorry. All right. I didn't know this. All right. We have more than one nothing. All right, Rich, put up your two nothings. We'll look at them.
Okay, well, you take space, you get rid of the atoms, you get rid of the people in the room, you get rid of the air, you get rid of the photons that are flying around, and you get empty space, which is the vacuum. And this is what a lot of people think about when they think about nothing, big, empty, dark, we heard big, empty, dark space. That's a quantum vacuum state. And if you want to visualize that, just close your eyes. Okay? That's what it looks like. It's black, okay? It has a color, it's black. Now, that's what empty space looks like. It's alive with virtual particles and things. It has fields in it. Larry will tell you about that.
Wait, Rich, I have to interrupt for a moment. Before quantum physics was discovered and developed in the 1920s,
yes.
Your concept of no matter, no energy, no particles, no people, there was no place else to go after that.
Well, Einstein thought empty space was empty, and you had geometry. So you had Einstein's field equations where you say, here's how stuff that you're talking about, curves, space, and time. And over here you could put a 0, and then you get equations that would tell you how space and time was curved. So space and time were still there, but there was 0 energy density in there.
Okay, so quantum physics stuck energy into that the classical physics could not, or didn't know to do.
It stuck the possibility of it there. Okay. And I mean, it could be 0, and still you have interesting virtual particles and things. Physicists were quite used to thinking of a vacuum as 0 energy density, but quantum mechanics also allows you to have a non-zero energy density. And if you have a non-zero energy density, that means some energy per cubic centimeter, you have also accompanied with that a negative pressure, because the laws of special relativity tell you that if everybody who flies through this in a spaceship is going to see the same energy density, no matter what velocity they're traveling at, then you have to have a negative pressure. That's just how pressure and energy transform in special relativity. Now, positive pressure, you got that in the tires of your car. It pushes out. Negative pressure is like a suction. But we have a positive pressure in this room of 15 pounds per square inch. But
the weight of the atmosphere.
Air pressure. But we don't feel it because it's constant. It's not blowing us one way or the other because the pressure is the same all over. So in the universe, if you have this quantum vacuum state that has a positive energy and a negative pressure, it's the same all over, so you don't notice it. Except that Einstein's field equations told you that pressure gravitates as well as energy, and so that negative pressure operating in 3 directions, x, y, and z, 3 spatial dimensions, produces more gravitational repulsion than the energy does gravitational attraction. So there's an overall repulsion. So this causes space and time to expand. We've actually seen this. This got the Nobel Prize recently for the discovery of the accelerated expansion of the universe because of this quantum vacuum state, because of the repulsion of this nothing, as you might say, this quantum vacuum state, the universe is expanding faster and faster.
So that's evidence that, in fact, empty space is not nothing.
That's right.
No, it's evidence that empty space is energy, not that it's not nothing. You look, you try and find out what's there. Try and measure particles or radiation.
If it's energy, doesn't nothing include something?
Well, you know, that I think you have to be a little careful. And Rich is right. The first definition of nothing, which I think is the biblical definition, is an infinite, dark, empty void. That empty void has energy, but it's still empty. There's no particles. You try and look in a region of space, take away all the particles, all the radiation. There's no stuff there, and that's nothing weighs something.
Larry, what about fields?
There are no fields. You can't measure them. There's nothing there.
It has a topology. It has a shape. It's a physical object. Empty space is a physical object. Wait,
I want to get back to that. Wait. Rich, you said that you take everything out of space, yet Einstein said there is still the geometry of the fabric of space-time.
Yes.
Do we have the right to say, because there is the fabric of space-time, even though it's not curved, it's just not bent by any actual matter, does that prevent us now from calling that nothing? Because we have a description for what it is as fabric of space-time.
Well, Einstein,
that's kind of what Jim's getting at, right, Jim?
Yeah.
Yeah, but that's the first kind of nothing. And then point is that's for a lot of people before physicists started talking about that kind of nothing having energy, they would have said that's a good enough definition of nothing for them, empty space. Now we know empty space is more complicated. So you might say that's not nothing. But then there's a next kind of nothing, which is no space at all. No space, no time.
Okay, so let's get back to Rich on that. So I think we agree that this classical understanding of nothing has been violated by our emergent understanding of Einstein's relativity and quantum physics.
And the first person to really say this was that this is Lemaitre said that Einstein's cosmological constant was really a vacuum energy state. He said this in 1934. So he's the first one to really identify with that. And another reason we identify that.
Lemaitre, he's the Belgian priest?
Yeah,
absolutely.
Mm-hmm. And physicist.
And physicist, yeah.
He proposed a model with the Big Bang at the beginning and a coasting phase, which we don't see, and an accelerating universe at the end. So of the early people, he got a lot right. Okay. So we also know there's an early stage of the universe where we had an accelerated expansion called inflation. And what we got today is a low energy version of inflation. This is a version where the energy density in the vacuum was very high. We're talking, like 10 to the 77 grams per cubic centimeter.
That's high.
That is high.
Yes, okay.
that makes a neutron star look ethereal,
Yeah,
I mean,
like,
that is a high density. Okay?
yeah. Just
Now-
put everybody on the same page.
Okay,
if you take neutron star density and make a volume the size of Thor's hammer out of it, it'll cram a herd of 300 billion elephants into that volume of Thor's hammer. So proceed.
So this is very dense. It's expanding very fast. It's doubling in size every 10 to the minus 35 seconds. And as it expands, the energy density stays the same in this vacuum state, so it makes more of itself. And another interesting thing happens. Two observers in this are separated so fast by the stretching space in between them that the light beams can't make it from here to here anymore. So event horizons occur. There's parts of the universe that you cannot see. This causes Hawking radiation. Gibbons and Hawking predicted this for this inflationary state.
The Stephen Hawking.
Stephen Hawking. He did this right after he did the black hole radiation. He said, in the universe, if you have an inflating state, you're going to have this Hawking radiation also. So if you live back there in that nothing, you're going to see hot thermal radiation, hot Hawking radiation. It's very hot. It's 10 to the 22 Kelvin. This is very hot.
Yes, very hot. Yes.
I mean, so the tidal forces are very large. They'll tear you apart in 10 to the minus 35 seconds. The gamma rays.
Have a nice day. Yeah, right, Rich.
The gamma rays.
Rich,
will
is any
burn
good
you
news
up.
in this? Right.
But the gamma rays will burn you up, and you will. I'll tell you what it looks like for a brief instant. Well, it looks blindingly bright blue because thermal radiation, would look bright blue. So it's we could say it's a quantum vacuum state. It's nothing, but it looks violently not nothing. Okay. Now the third, or the second nothing that I was talking about.
Can I just jump in on that? Eva, you've worked a lot on. Eva, you've worked a lot on this early inflation epoch,
Sure.
very early in the universe.
Right.
And when I think of that inflation era, doesn't that come from a time where there is no structure, but then we have structure now? Is that kind of something out of a nothing scenario?
I think so. I think that's what Richard was about to get to. You start with these fields in the lowest energy state that they have. And the system is expanding rapidly, exponentially, in the way he was just describing. And that time dependence of the energy function is enough to take a system which starts in its ground state and excite it. It's not really any more complicated than that, but it's a beautiful theory of the origin of structure and testable. So.
And one of the neatest parts of it, which we don't celebrate enough, because we talk a lot, and probably you've had, I don't know if there are any of the sessions, about macroscopic quantum mechanics, which is the big thing, quantum computing. Wouldn't it be great to have quantum mechanics on macroscopic scales? The really neat thing, the most amazing miracle of inflation, is it takes quantum mechanics and turns it into us. It's quantum fluctuations that become galaxies and us. It's the most macroscopic quantum mechanics you can imagine. It is amazing. And it does it in a very simple way. It turns quantum mechanic fluctuations into density fluctuations in a simple and beautiful way. It's amazing, and we should celebrate it.
So I wanted to make one more comment about this discussion of the definition. So it's possible as a theorist to separate issues a little bit and think about turning off gravity but keeping quantum mechanics. And then you can make a very precise statement about what the ground state of a system is.
But you do this in your office? You turn off
You
gravity?
do this in your-
You turn on quantum mechanics? You just do this?
You do.
It's California.
It's California. These theorists, they're lords of the cosmos. Go on.
We don't have the budget for gravity, you know.
Go on. Turn off gravity. We have a quantum universe. Go on.
Right, I'm just trying to separate that. I'm trying to say quantum mechanics, you know, with just quantum mechanics, you can define what you mean by the vacuum state, the zero energy state. You can even consider, to be a little bit more mathematically precise, what we call a gapped system, a system for which it takes a finite energy to excite it. And I think that's also a pretty good definition of nothing. In fact, according to some of our modern theories, which relate non-gravitational physics to a dual description in terms of gravity, the two are closely related.
I'm betting that Jim Holt doesn't agree with your definition of nothing.
Well, I was going to.
Oh, okay. You have a third nothing.
Well,
No, I have a third nothing.
Wait. Just, Jim, react to Eva.
Listen, the only even remotely persuasive definition of nothing I've heard from a physicist came from Alex Vilenkin, who said, you know, imagine a closed spherical space-time. Imagine the surface of a ball. It's a finite space, but it doesn't have any boundaries. Now imagine the ball shrinking down to a point. Its radius goes from finite, shrinks down to zero. So now you have a closed space-time of zero radius. This was Alex Vilenkin's definition of nothingness. And he did some quantum mechanical computations and showed that given a closed space-time of zero radius, there's a finite probability that a little nugget of false vacuum will spontaneously appear, will nucleate out of that, and that, by the miracle of inflation, will evolve into the world we see around us. And I think that's a really nice story. But there are two problems with it. One problem is a closed finite, a closed space-time of zero radius, is that really nothing? Well, there's no space and there's no time, so anything that exists in space-time can't be a part of it. But what about physical laws? What about mathematical entities? What about, you know, consciousness, value, all the things that are possibly non-spatial, non-temporal? Those aren't ruled out, so it seems to me that the notion of nothingness is a very parochial
We'll get back. You raise a really important point that I want to get back to. What you're saying is you could have a universe that's got nothing in it, but if laws of physics still apply in that universe, the laws of physics are not nothing.
Yeah, where are the laws of physics?
Okay, so this is a very interesting way to approach the problem. Take a space-time and shrink it. The problem is that general relativity, the description based on that, breaks down. Exactly. And now you need a theory that goes beyond it. There are candidates for this. The leading one is string theory, and let's talk about this briefly in string theory. Zero radius does not mean nothing in string theory. In some cases, in fact, it's equivalent to large radius for a cute reason having to do with light modes from strings winding around the small radius. But more generally, you can go where you're going instead by asking how many effective dimensions do you have? And you can ask that question by counting the density of states of the system that are available. And shrinking a space to zero radius does not necessarily reduce the number of effective dimensions in that sense. There are processes which do that. These are processes which appear in topology changing transitions and in some resolutions of singularities in string theory. But it's a technical question that you're asking, and you can improve on that answer.
But we're all whistling in the dark here. I mean, we don't have a final theory.
Of course we don't. Of course we don't. But we still have some rules, and we try to.
Rich, let me get back to your third.
Oh, okay.
Your third nothing.
Well, that's a second nothing there. The zero universe, and Leasingly and I didn't think that was exactly nothing. It's a quantum state. It knows about the laws of quantum mechanics and so forth. You know, so we did not think that was exactly nothing. So the third one is what I would call really nothing. No quantum state, no nothing. You know, and I want to tell you what that looks like. Okay.
Wait, you just said no nothing.
Well. Okay, that's bad.
I'm just trying to, our vocabulary is going to start mattering really badly, as we go forward.
Grammarians will correct.
So don't tell me the nothing you're about to describe is not nothing. That point, yeah. Okay, go.
Okay, so what does really nothing look like? Well, what does it look like back here? Is there a big black thing back here? A big black cape over here on here? No. not Neo.
Okay, I'll stand over here. Now repeat that. Go. Okay.
It's not black back there. You don't have any retinal cells, looking in that direction. So that's really nothing. It's not anything. It's not there. And so Li-Jing Li and I thought that of Lincoln's model, which we thought was very interesting, what they're trying to do there is make quantum tunneling is weird. You can be in the room and then tunnel out without going through the wall, that kind of thing. It's weird, and so we are looking for something weird to start the universe.
Wait, just to get people on the same page of quantum tunneling. So quantum tunneling, if it happened in the real world, you'd be on one side of a mountain, and rather than having to climb up the mountain, come down the other side, you would instantaneously just appear on the other side. And quantum particles do this all the time. In fact, the sun cannot produce energy without a form of quantum tunneling, because there's a barrier in the way, and how do you get to the other side? And I think in the movie Buckaroo Banzai, in the 10th Dimension, he would go through mountains for just this way.
Oh, yeah.
Yeah, yeah. 3 of you saw that movie, apparently.
Great movie. It's about a rock star physicist. I like it.
He said, very wise, everywhere you go, there you are.
Exactly.
That's right. The quote of the movie, yes.
Great,
okay, so your nothing is not even anything, is what you're pointing at.
Yeah, and so we thought we'd try something different. We thought that it might be hard to make a universe out of nothing, particularly relying on something that by definition didn't exist. So we thought, well, maybe the universe isn't made out of nothing. It's made out of something. And that something could be itself. And so inflation allows you to do this. And
I knew there was something in there.
You knew there was something. Now this is the
Rich,
model.
do you have the universe in that Tupperware?
Never comes without a visual aid.
This is the model.
Universe in a Tupperware container, yes.
So here's a picture of our model. It looks like something Dr. Seuss invented. This glass represents space-time. We're showing one dimension of time going up this funnel here. This is an inflating universe here. The circumference is getting bigger as time goes up here. We're showing this is an inflating universe. And Linde, who's at Stanford, showed that quantum fluctuations that we've heard about can cause a universe to give birth to another universe here. And so this is a universe, baby universe, born. This is called chaotic inflation. This is a universe born by quantum fluctuations off of this one. It's a branch that grows up to be as big as this trunk, and then it can sprout branches of its own.
But so, Rich, you're holding in your hand 4 universes. Is that correct?
Dude, just 4.
Yeah.
Fine, okay.
Yeah. It's not heavy. They're my universe. These are 4 universes. Now, what intrigued Neil about this is that he say, well, what's outside here? What's this expanding into? Nothing. The only thing that's real here is the glass model itself. It's curved, it has a shape, but to visualize it, we put it in this background space, but the background space doesn't exist, just the glass itself. So here's a universe coming off here. So Li-Jing Li and I said, well, what about if one of the branches simply branched off here, circled back in time, and grew up to become the trunk? This is possible if you have a time travel solution in general relativity, of which they exist. It makes a little closed time loop here. And if you go, and the universe is inflating, so this branch gets bigger and bigger as it comes back here, and the trunk is bigger than the branch. And so if you're here and you went around this, you would be able to come back in time and visit the event where you were. This is a time travel to the past in general relativity. This is what this looks like. Every event here has events that preceded and caused it in the usual way. So if you're here, there's an earlier event here. There's an earlier event here. There's an earlier event here. And so if you go back in time, you go back further and further, and then you start going around. It's like the Earth has no easternmost point, although it has, it's finite toward the east. And so we thought this might be useful for addressing the, famous first cause problem. This universe is finite to the past, but it has no earliest event. And the interesting thing about this was that this geometry here explained the usual causal set of events we have where photons go only toward the future. If you shake a photon here, it goes out and intersects Alpha Centauri 4 years from now, because it's 4 light years away. Maxwell's equations allow what's called advanced waves that go to the past and would be shown intersecting Alpha Centauri 4 years ago. But we don't see them in nature. So it doesn't have anything to do with electrodynamics. It must have something to do with the beginning of the universe. So in this case, the only self-consistent solution for this is one where photons go toward the future. Because if you had one that came back here, it would come back here, go around an infinite amount of time, gaining energy all the time, and blow up and cause a singularity and not be the geometry you started with. That'd be like killing your grandmother. So you're not allowed to do that because you have to have a self-consistent solution. So it also explained the entropy area of time because this was cold.
Wait, so you're creating the universe out of itself rather than out of nothing?
Yes, we were asking the question, can the laws of physics allow the universe to create itself?
Are there laws of physics out here?
No.
There's nothing out there.
That's
so
real.
Okay, you happy with that?
No,
It's
I'm
not
not
even-
happy. What tells the abyss that it's pregnant with this thing?
That's,
it's finite in time. Every event has a cause. There's no first moment. Why does it exist? It exists eternally.
Mr. Leibniz would say, and listen, Leibniz's answer was God. Leibniz, as they say, smart guy, invented calculus. Leibniz's question was, why is there something rather than nothing? We were just trying to answer the question, how did the universe get here? So if we say, given that the universe is here, how did it get here? This was a possible way to do it.
So, Rich, your universe always was. That's your answer.
Well, if I think four-dimensionally, like Einstein, I'd say I got this four-dimensional sculpture here that doesn't change. It's a four-dimensional thing. It exists. And so Mr. Leibniz would rightly ask, so why is it there? Instead of not there.
Or instead of something else.
Well,
wait.
That evolved according to a completely different set
That's
of
what
laws.
he would
Yeah.
Charles,
say if
Charles,
we were here.
we've
We
got-
didn't claim to answer that.
Charles, in your study of zero, you studied Eastern philosophy, right? And we have some people arguing over here about basically first causes, right? And I'm just curious, I don't study Eastern philosophy. Around the world, are people as disturbed at the need to have a first cause? Because that's what's driving all this. It's like, well, how did it get here? I have to know. It is a problem to be solved. Is there anyone in the world who's just cool with that?
I can't say I've studied philosophy as extensively as to answer that universally, but almost all mythologies.
University mean earthwide.
Earthwide.
In this house, universe means the universe, okay? So, like Miss Universe? No, she's Miss Earth, all right? Let's just establish that fact now.
Well,
Continue.
this Earth has the home planet advantage, so that's not fair.
That's right.
But basically every mythology, more or less, needs a creation mythos of some sort. Basically, two functions of a mythology are explaining where we came from and where we're going. And
So the urge was there.
the urge was there. The urge was there.
Pre-scientific era.
but let me look. We don't need the point is science doesn't worry about a first cause. I mean, you're pretending it does, but it doesn't. Religion does. First of all, there are lots of good physical definitions of nothing, and I still think the best physical definition of nothing is the absence of something. So to understand nothing, you have to
So we're
understand.
done.
Yeah, you have to understand what something is. That's why it's a physical question and not a philosophical one. First, you have to understand what something is, and you have to understand what the absence of that is. All those are physical questions, and physicists try to answer them. Now, there are a number of different answers which we can get to, and Rich has talked about some of them. There's still the simplest thing is not to take to zero radius, which is, as Eva pointed out, is not physical. At least most of us think it's not physical. When you apply quantum mechanics to gravity, and we don't have a quantum gravity theory yet. Some people think we might be getting close, but we don't know if it is. But one of the things is quantum mechanics says things fluctuate. And if gravity is a theory of space and time, if you make space and time quantum mechanical variables, then it is perfectly possible for universes to pop into existence. Space and time to pop into existence where there was no space and time before.
Hold on.
Now, hold on. I haven't had a chance to talk yet.
I must ask you a question here.
What?
Space and time pop into existence. You make that sound like a temporal process, a process in time.
Well, because I
It's
said
not
so
a
you could
process in
understand
time.
it.
Huh?
No, I mean, I used words, and the problem with words are, as T.S. Eliot says, they're sort of slippery.
Right.
Okay, how about this?
But becoming
Well, I know where he's
implies
going.
time. You can't have time coming into existence
Yeah.
as itself a temporal process. That makes no sense.
well,
That's
you
why
pop-
it's good
you
to have
create a
philosophers
closed-
around, which I'm
you
not one
create
to
a
help
closed-
you use language precisely.
And so let me just pretend there. Let me just say that there's a global time, and at some time a space pops into existence.
I bet
Okay,
you
will that
can't
make
say.
you happier?
Okay, there's
Okay,
a global
but-
time, and then
Just
there's
to,
a...
just to clarify.
But the
Yeah, yeah,
point-
yeah.
Wait, I have
the
to,
key-
Okay.
just so I understand what's
We
going
have
on.
how many
So wait,
nothings do we have? Global time. And
hold on, just so I understand what's going on. Lawrence, you are saying that because we are illuminated by the actions of quantum physics, mentally, we can think about whatever is our best understanding of nothing, and quantum physics then pops into existence in that nothing an entire universe. And if that's the case, I would then pick up Jim's point and ask
I
you...
was going to try and ask, where did the quantum physics come from?
No,
Is that what you're gonna ask?
that's not what I'm going to ask you. I'm going to
Okay.
ask you, that had to happen at some point.
Why?
Why isn't it happening all the time,
It can
everywhere,
be.
at all times?
First of all, it can be, and it wouldn't be noticeable at all. Okay, it could be happening in our universe. You'd be popping off baby universes, but they would disappear from our universe.
Okay, why don't you like
them.
his nothing that he built his universe in?
But that's, okay.
Why don't you like his nothing? That sounded like a good
Well, first
nothing.
of all, as he himself admits, his nothing is a something. And
Well,
when you start with a
what is the
contradiction, you
something?
can derive anything.
Let me get to the point.
Go.
The key point is this question. First of all,
It's
the
a
question,
physical
why is there
object,
something...
it has structure, it obeys laws,
Hold
complex
up,
laws, there's a lot of
hold-
stuff going on.
hold-
I mean, my bank account, where there's no money in it, is still something. And,
Yeah,
and the
absolutely.
vacuum is a hell of a lot more of something
okay,
than my
but-
bank account.
Okay, well, no, the point is that the key question is really, the why question is stupid. Okay, everyone who has kids knows that.
Wait, which
No, no,
why
because
question are you talking about?
eventually you keep saying, why? The only answer is go to bed. Okay? and so the point is that what we really mean is how. That's what when we say why, what we really mean is how. We care how did it happen. Now the question isn't, was there something else that existed? The really amazing thing, the question that really matters, and it may not be the question that matters to some classical philosophers, but it's the question that really matters is, how did a universe of 400 billion galaxies containing 100 billion stars, how did that come into existence if there weren't galaxies, if there weren't stars, if there wasn't energy? And that is the question that physics is coming close to answering. And that may not be the ultimate question of whether there was nothing before that, but there was nothing, our universe didn't exist. And our universe coming into existence when it wasn't there in the beginning with zero energy, but still enough gravity to create everything we see is the amazing, remarkable miracle that science creates. And that's the important question.
Yeah, it's a great story. There's lots of empirical evidence for it. You've told a miraculous story about how a universe like ours was spawned by a piece of rubber. But where did the piece of rubber come from?
No, and the point is that even the laws don't have to exist. There could be in the multiverse.
Wait. You said a quantum fluctuation brings the universe into existence.
That's because I can talk in our universe about quantum mechanics, but it could be, although this is wild.
Nothing else we've been talking about until now is wild, but this is wild. Okay,
yeah,
go.
This is even wilder. Okay, so it's quite plausible. In fact, if there are many universes, as current theory suggests, that in each of them, the laws of physics essentially come into existence when the universe comes into existence. There are different laws of physics
then
in
you
each
can't
universe.
invoke a quantum fluctuation
but
to
maybe,
give you the universe
but I
that has
don't know,
quantum fluctuations.
But what is interesting to me, and I have no mathematical underlying theory of this, but it's perfectly possible, it seems to me, that some of those universes don't have quantum mechanics. I don't know if quantum mechanics arose when our universe arose.
Ava, I keep calling you Ava.
I mean, I can only describe it mathematically by a theory right now, but I don't know, String theory is
Okay,
quantum field theory
okay.
applied.
I met
Okay.
Eva on the campus of Stanford a couple of months ago when I happened to be in town. And first time I met her, and she had already been invited to this, and we just chatted about nothing. And so she went on, and so it was something, but it was nothing, right? So we're chatting on, and then at one point, she described a nothing to me that just blew my mind. Okay, so Eva, could you give it, because the nothing you described to me just would send all of us home in 3 minutes, okay, because we're done after the nothing you described to me. I was like, I went out saying, damn, I can't even. So could you please just.
I'm not sure I could live down to that, but I'll try.
Okay, just to give me that nothing, and you all just shut up and listen to this. Okay, go. Go.
Well, so I already said
I'll get a close listen on this. Okay, go.
All right. I already said my conservative view of nothing, which is inflationary density perturbations, but let me come to this more ambitious question that's being discussed. And there is a model, I think, for what you're referring to. It happens to be a model within string theory, but maybe there would be more general approaches to that, which basically proceeds as follows. So space-time is an emergent thing. Large radius space-time is what we think is rather special. It's the exception rather than the rule. And it can evolve toward a singularity or evolve out of a singularity. But let's consider the case where it's evolving toward a singularity. And what can happen is time can keep going forever. But in effect, the masses of all the fields, including the graviton, exponentially grow. So there's a pretty controlled model of this in string theory. It's a classical version of what is called the Hartle-Hawking wave function. And so, we can make sense of that. We can do computations of, if we assume we're in the vacuum in this exponentially massive phase, we can ask, what does that state correspond to in the time periods when there is a large space-time? So we get an answer for that. It's a simple thermal distribution of particles. So, these are questions that we can begin to try and address using technical tools that we're developing. We're far from answering the ultimate questions. No one would ever say otherwise. But I don't think
the fact that it's implausible is what's
Well, no,
really
you described something about dimensions and it went away?
Yes.
You're getting there. Okay.
Well, that's right. So as you... Okay, so...